When you need a device to push more power, the most intuitive fix is to simply stack batteries end to end. By chaining them together, you increase the total electrical pressure, or voltage, driving the circuit. This diagram shows a standard series circuit with n identical cells. To find the total current, denoted as I, we divide the total voltage by the total resistance. Since the cells are in series, their electromotive forces, or EMFs, add up to NE. But remember, every battery has its own internal resistance, R, which also stacks up. So the denominator becomes the external resistance R plus NR. A common mistake happens when batteries are installed backward. If M cells have their polarity reversed, they actively oppose the forward-facing cells. This is why we subtract 2M in the formula. One M cancels out a forward-facing cell's contribution, and the second M represents that same cell now actively pushing against the current flow. This visual shows two non-identical cells in series, E1 and E2, proving the same logic applies. If their positive and negative terminals align properly, we add their EMFs together. If they clash, as seen in the bottom circuit, we subtract the weaker cell from the stronger one. In series circuits, everything stacks. Because the environment is strictly additive, a single reversed battery forces a double subtraction that can significantly diminish the circuit's total driving force. This diagram shows identical cells stacked side by side in a parallel configuration. While series circuits boost voltage, parallel setups maintain a single E while dividing the total internal resistance by the number of branches, N. This makes parallel configurations useful for reducing internal resistance. But things get complicated if you place batteries with different voltages in parallel. As you can see in this breakdown, calculating the current manually forces you to set up multiple tedious Kirchhoff loop equations to track exactly how the different voltages interact. We can bypass those long derivations entirely. This screen highlights the equivalent formulas. By calculating an equivalent EMF and an equivalent internal resistance, you can mathematically compress the entire messy parallel block into a single imaginary superbattery. Let's test this with a 3-branch parallel circuit. This diagram presents a 20-volt, an 18-volt, and a 12-volt battery, all with different internal resistances. Pause the video here and try to calculate the equivalent EMF. Pay close attention to the orientation of the middle battery. Let's break down the math on the right. We divide each cell's voltage by its internal resistance and sum them up. Because the middle battery is flipped, its voltage actively opposes the other two, so it becomes a negative value in our numerator. Solving the fractions leaves us with an equivalent EMF of 11 volts, reducing the 3 branches to a single path. Resolving parallel configurations is an exercise in calculating weighted averages. A reversed battery acts as a mathematical anchor, dragging the system's overall equivalent voltage down. For our final problem, let's find the total current running through this entire circuit. This diagram presents two mismatched parallel cells, 10 volts and 5 volts, connected to a large 10-ohm external resistor. First, we temporarily ignore the external resistor and focus entirely on collapsing the parallel cells. Using our shortcut formula, we add 10/2 to 5/1 and divide by the sum of their inverted internal resistances. This compresses the parallel section down to an equivalent EMF of 20/3 volts. Now for the step that often trips students up. To find the final total current, you must add that 10-ohm external resistor back to the newly calculated equivalent internal resistance. Once you have the true total resistance, Ohm's law yields a final current of 5/8 amperes. To consolidate these rules, here is a reference matrix comparing series and parallel circuits. The rows represent the circuit type, while the columns separate identical and non-identical cells. Notice the subtraction signs. These identify exactly where the math changes whenever a battery's polarity is reversed. No matter how complex or mismatched a battery pack appears, the strategy remains the same. By systematically reducing branches to a single equivalent battery, you can rely on standard Ohm's law to solve any circuit.